Should be on right now. Yes. All right. Yeah. So apologies, class. I'm still quite a bit sick from like virus imported from the baby. The I guess the advantage of an online class is that I don't need to be worried about like transmitting the viruses to you. Anyhow, so yeah, my voice could be breaking in the middle of this, but we'll manage like last time. So couple of quick announcements or prelude before we move on. We're still going to talk about sequential data. As you can see that there's lots of good jokes if you work with sequences as well. So our contact hour. So next week there's no tutorial. We've set aside 3 of the tutorial slots as contact hours. You're welcome to come in person or meet the tutors online. And beyond next week, so basically week 13, before our exam in, I'm just going to call it week 14 for now. We are also going to have 2 slots, basically the Thursday and the Monday just before the exam. Rooms are being booked. So yeah, we are happy to help you with any of your usual pre-exam questions then there and then. So I might like come to one of the sessions and there will be at least 2 tutors in both in person and online sessions so that people studying both remotely and in person will get attention. And we'll talk about the final exam next Monday, along with a number of other concluding thoughts. All right. And the other outro today is surveys, right? So I believe this for most of you, vast majority of you, it wouldn't be your first semester at the ANU. So you know that the official survey is called SELT, Student Evaluation of Learning and Teaching, I believe. So have a look at the website with resources. Basically, you'll get an email when the survey is open fairly soon or not, if not already. And it also shows up on your Wattle as a survey block. So please fill it in to help us and the tutors improve for next year and for your future self or for your other students. Basically, it's a pay forward system. There's also a couple of videos in case you want a refresher about how to fill in the feedback so that it's most useful for everyone. I promised that we'll talk about our informal in-class survey. So here it is. Thanks to the 20s all students who have filled in the survey. So what I read from it is that, for example, people are reading the textbook quite a lot, and also, or at least people who filled in the survey are using this workshop and the 2020 lecture videos. The tutorials, some people left a comment saying that it's good, but overall it's been a mix. Again, this is a sample of 20-something in a class of 180, so take it with plenty of grains of salt. And in terms of where you guys felt you learned, so right, the textbook and 2 sets of lectures / workshops scores sort of slightly to the right or the higher side. People seem to have learned quite a bit from assignments. They are of various levels of challengingness. And some people learned a lot from tutorials. Some people didn't learn much from the tutorials. Again, and there were a free text comment from a student saying that if you prepare for the tutorials, you tend to find it more useful. So that's interesting. So here is a non-random selection of the things that you guys said. I'm just posting here for you to read. One thing, so there's several things that this exposed for us, and myself in particular will use this to think about what to adjust in the next time this class is offered, right? So the primary thing I would say is I see a diversity of experiences, basically. So, for example, there are comments saying that the textbook is great, having 3 passes at the material is great, following the textbook is great. And then there are also comments saying Bishop isn't a great textbook with reasons. So I would say in defense of the choice of the textbook, there are concerns about notations in this textbook. I would say I haven't seen anything better in terms of notation consistency. And after all, so I would even go so far to saying that one of the main reasons that you follow a class like this, rather than just go on doing your own learning from different online materials and textbook, is sort of basically normalized and explained notations, and also, of course, a selection and sequencing of the content, right? After all, this is a upper level university class. The learning happens in you. We're just here to help, right? So people seem to have, a few people liked the breadth and the mathematical nature of the content. And then there are people asking for more proofs in the video. There are also a comment saying it is a bit too mathematical and it will be great to see more code, or basically talk in terms of code rather than symbols. I would say that the perspective here is mathematical and symbolic thinking in terms of statistical machine learning, we feel is important for the conceptual understanding of the field. And also, this is also the language of the research community in SML. I very much acknowledge there is basically a translation, a non-trivial translation between the mathematical and symbolic thinking to implementation. As you guys would have known in assignment 1, basically between tutors and myself, we had a long discussion about what is exactly the purpose of the assignment, right? Should we basically write the assignment also in the mathematical and symbolic way and then expect you to translate into code? Or should we just basically provide a bridge between the math and the actual code and give you another set of symbols for you to digest? So we settled on that. So I'm also aware there are other classes on machine learning that are taught with code being featured as the more prominent tool, right? So if, for example, if you're doing an HMM, here is the recursion code that you're going to write, and by looking at the code, you should be able to map back to your conceptual understanding. We choose not to do that, I guess, in this class. But if I'm also aware that a large number of students, a non-trivial fraction of students, prefer to think in code. If this is you, I'm afraid that, well, you have to go rely on some other material or come to talk to us. We're always happy to give you pointers to code to look at, right? For example, sklearn is a great package with many of the things that we talked about implemented in code. And again, I personally prefer not to teach in code. I think that's a conscious choice I have made, which may not work for every single student. So there are comments about whether so the perpetual struggle of still intro to machine learning class is what to cover within this bounded amount of time. And also within the AU, we're also told to limit the course workload to about 10 hours per week. So we can focus more on the theory questions, or we could choose to maybe include a bit more practical work next year. I think I have enough to reflect on the balance this year, and especially in the environment of blended or online learning, which is new for us as well. Right, so some of you asked for less content and more like deeper content, more proofs and so on. I feel that next year we're going to, right, we can't go back and change this year. So there should be so there's a couple of things we could try. So non-zero mentions of practical aspects and implementation. In fact, on next Monday, I'm going to talk about some of the practical aspects, although that's still above the level of specific code. In terms of depth versus breadth, I feel in terms of the amount of content, this is as much as we can cover. We probably can rotate through different contents, basically cover less of something, and replace some of the content. There's plenty of other great material in the book, such as Gaussian processes, approximate inference, and so on, that we didn't touch on. Another thing that's missing this year is guest lectures, right? Or what is a taste of what research or what you could do with these. This class traditionally has one, and this year we didn't have any in part because of this overlap with 3 public holidays. We could consider including those. And if you're still with the ANU, you're more than welcome to attend seminars, research seminars that serve us. I think they're a more realistic picture of what research is around the area is than guest lectures. So there is AI plus machine learning plus friends seminar series that people can just subscribe to, and all of the seminars are also available on Zoom right now. So that's as much as I wanted to say about our course survey. Feel free to continue to write to us if you have comments and so on. So unless people have immediate follow-up questions, I'm going to delve into our agenda for today. This is just the same table of contents you've seen, I believe. So remember last time we talked about learning hidden Markov models and inference, but we essentially left a gap. We said, oh, we assume we have these posterior variables, and now let's do the M step in EM. So we're going to spend the majority of the time today walking through the E step of hidden Markov models. So just as a brief recap, on Monday we talked about the graphical model representation of hidden Markov models that essentially involves unrolling a Markov chain over time, and where in each time slice there is a hidden variable, latent variable, and there's an observed variable that depend on the latent variable. We saw 3 different representations of the SGMM. This other one is called the lattice representation, which is particularly useful today. So all of these squares are values of these latent variables in different colors, and the unrolling over time is the same. The advantage of this lattice structure is that it allows us to visualize these transition probabilities, which are useful in the recursion that we will see. So the observations X is sort of implicit. They sort of sits on top of each state, if you will. So this was where we were hand waving last time. So we say we would like these gamma variables to be the posterior probability of being in a particular state z at time step n, given theta, the model parameters, and x, the observation sequences. We also said that we have the posterior transition probability, essentially, not quite the transition, but the posterior join probability of two states in the digestion time steps, defined as C. Because these ZNs are vectors, it's good to have us define notations for the elements of this vector. Basically, the gamma of Zn and K is the probability of being, like Zn takes the K's value given the above, right? Given the same thing. And the later two steps are simply writing out what this means using the one of K encoding that we have been using. Similarly for the C term, so in this C, which is a matrix, the J and K's entry is basically the joint probability of being in the K state preceded by the J state, given the observation sequence. Right, so we can imagine basically a mental picture for this C term is basically if we say this is J, J's term and K's term, and then the C term of Zn minus 1 and J's in the J state and Zn in the K state describes like some score of this edge at a given time step, right? Similarly, the gamma term describes, right? So the gamma term, you can imagine it's a score that sits on the nth time step. So basically, every one of these state space squares will have a gamma score, so to speak. And then on every edge, you would have a C score. Right. So this is one view of how the lattice structure is useful. Now let's try and like just re-look at why computing them is hard. Right. So now if we do what we did, remember the example of basically two uni students. Peter is a student in Canberra who reported that his activities on a daily basis were cycle in both, right? Cycle, shop, and study. And there's which thing he does depend on the weather, and the weather is, say, a latent variable for a student in Sydney. So in order to compute, let's say, this C of Z1 equals rainy, and then Z2 equals sunny. Given this observations variable, we will need to sum over basically the state sequences that are like rainy, sunny, rainy, and rainy, sunny, sunny. And that's conditioned on there is nothing that precedes so these are the valid state sequences. There's nothing that precedes that one. So if this were a much longer sequence, such as speech, we will have to expand. So these are the expanded part of the state sequence. We basically have to expand all the preceding valid states and all the trailing valid states. As you can see, you are all CS students. You can see this is an exponential blow up with respect to the state size of the state space, where the exponent is the number of time steps. Right. So this is order of kt or big N order of. Here we use big N kind of operation. Similarly for the gammas. So we're going to talk about a famous algorithm called the forward-backward algorithm. It is the most direct kind of inference algorithm for HMM, and we will, after we talk about it, we will talk about how it relates to some product, or basically directly maps to some product. So we want to efficiently evaluate gamma and Xi. We notice that the graphical model for the HMM is a tree, and we should make use of that. Well, we already know some products, so we know that for tree structured graphical models, efficient inference algorithm exist. One sort of slight catch is that this tree is of bounded but not fixed length, right? So we know that given a graphical model, we can which is tree with no number of nodes, we can perform an inference. The main catch here, the HMM is a sequence that grows, right? So if the sequence can potentially be arbitrarily long, can we still perform efficient inference? The answer is yes. So this famous algorithm is called forward-backward algorithm. It's documented famously by Rabina in 1989. This is a tutorial paper. I can tell you that this is a great tutorial. I personally learned about the forward-backward algorithm from it when I was a grad student. And this algorithm was proposed, well, not like alone, or Baum-Welsh was, it's called the Baum-Welsh algorithm and proposed in the 70s. Again, these are documentations about speech recognition. But the tutorial itself, for example, isn't written just for speech. It's written for a general inference algorithm. It's very readable. As you can see, these predates some product algorithm, right? I would even argue that they inspired some product algorithm and many similar subsequent algorithms. They're really very well known. So there are different variants of this. There are so many variants of forward-backward, and the difference is usually in the form of the message propagated. So the variant we look at is called the alpha-beta algorithm. Well, in essence, what this means is actually the same as the one covered by Rabina. So the alpha are called forward variables, and the beta are called backward variables. There is a one-to-one relationship. So I would say for HMMs, if you mention to another researcher that you're using forward backward, it's probably more known than if you say alpha beta, but it's just names. In order to do that, we're going to make use of some conditional independence relationships in the HMM. The first one we will look at in more detail in the next step. So these are all listed in the book, and the book recommends that you go and check each of them using the D-separation terminology. I think it's great practice. So, for example, if we look at the second one, it says, right, so the first n-1 observation is conditioned on the nth observation, and the nth hidden state is equivalent to the first n-1 observations considered conditioned on the hidden state alone. So what this means is basically x1 through n-1 is conditionally independent of xn, given Zn, right? We can see this is true because, well, the dependence in and out of Zn is in the head-to-tail pattern, right? And Zn d-separates any of these and Xn. So similarly for the next one below, Zn minus 1, also d separates these and Xn. And Zn itself, right? So this is the head and, actually tail pattern in the d-separation. So for the first expression, the claim is that in an HMM, the first n observations conditioned on Zn. Basically, Zn d-separates the first n observations and also all subsequent observations. So this is, so let's look at this a bit more. Any path from the set x1 through xn to the set of subsequent observations goes through Z. Right, so if we moralize this graph, there's no co-parent, we just remove all the arrows. This set and that set, they are connected through Z, right? And Z is observed, it's conditioned on. So all paths of these are head to tail, and all the paths from any of these x's before to the x's after are blocked by Z. Right? Therefore, the conditional independence holds. Okay, great. So for a potentially sort of arbitrary long sequence, now we can separate this data likelihood term, which is kind of nasty because we wanted to marginalize all the hidden state sequences. We can basically say that we can separate into two parts, conditioned on Z, right? So let's make use of this fact, right? So the expression from the last page is here, right? P of x given Zn, right? And we wanted to we wanted to relate this to the gamma variable, right? The gamma variable is posterior of Z given x. So we use the base rule to just flip this, right? So we write it as P of x given Zn times P of Zn over the data likelihood P of x, which we don't know how to compute yet, but let's just assume we have it, right? So there we go. And we use, this was the expression from the last page rewritten. So we expand the first term here using this decomposition. We simply rewrite everything, and then we basically move the term using, again, the sum product rule, P of Zn into the first term, right? So we now have the joint probability of x1 through xn and Zn times the conditional probability of all the subsequent x's conditioned on the Zn over P of x. Okay, we just did some simple base rule manipulation. Now, right, okay, so that's the real work for this page, right? Despite there's lots of symbols. And now we just proceed by defining two symbols. One is the forward variable alpha, the other one is the backward variable beta. So this step has no real work involved. Where alpha is basically a probability of observing the first n observations and Zn, and beta just the probabilities of all future observations given Zn. Okay, that's all. So we worked a bit using some sum and product rule. And now we have a variable called alpha and beta. So that's a promising step, right? So just a recap, here are the definitions of alpha and beta. We will want to show, like in the next page, that there is a recursive relationship that holds for the alphas and also the betas. We can first see how we compute alpha 1, right? So alpha z1 is probability of x1 z1, right? We know that the probability of z1 is distributed according to the prior probabilities pi, and then x1 condition on z1, right? So trivially this decomposes into x1 condition on z1 and times z1. The probability of x1 condition on z1 is basically p of x1 given the parameters associated with state k. So they're phi. Think of them as Gaussians or discrete. And because this is vector notation, we just raise to the power of this indicator variable. Okay, so here's the recursion bit, right? So we use the definition of alpha zn, rewrite it here. We pull out the zn and do this as a conditional again. And then the hint here is that we wanted to basically express we want a recursion, so we want to express the alpha zn in terms of alpha zn minus 1, like the alphas of the previous time step. And also the transition probabilities A. The initial probability pi don't apply unless we're talking about the first alpha. So we want the A and the phi, possibly the phi in the expression, right? So let's try and move towards the direction. So notice that we have x1 through xn here, so we try to pull out the xn from this, which is this term. And now we end up with x1 through xn minus 1 conditional zn times p of zn. Okay, these are all some base rule manipulations. Now, like from this step onwards, we want to involve, right, zn minus 1 because that's in the definitions of alpha zn minus 1. So therefore, we notice if zn minus 1 doesn't appear, we add it back and then marginalize it out. So this is what this next expression does. And now what we want to do is we want to move, again, base rule, move the zn minus 1 of being conditioned on. And it turns out that because of the deseparation properties, we can pull out basically this z of n conditioned on zn minus 1. And this is a familiar term, basically all the state sequences conditioned on up to n minus 1 condition on zn minus 1. And because the way we constructed the alphas, which is not a conditional but a join, the hint is to put this one back in here, right? So after these manipulations, well, like we're not going through this sequentially, but just picking a few spots. If you want to go through it sequentially, the recursion relation is basically as follows. We're going to look at it again graphically in a little bit. Alpha zn is basically alpha of zn minus 1 times the transitions, like summed over all the possible incoming states, zn minus 1. And then these are the phis, right? These are the probabilities of the observation and step n. So alpha of z1 we already talked about. Okay, so that's a lot of notations. Graphically, what this means is that we can now imagine, recall the trellis representation, right? We can now make alphas as like one set of scores that sits on each node, each state in the trellis. And then if we would like to compute alpha z for state 1, we basically look over all the alpha z and minus 1s for all the states. Right, we look at each of them. For each state, we use the previous score to multiply with the transition probability, the corresponding transition probability. So we get 3 products. We sum over z and minus 1, and then we multiply by the emission probability. You can think of these as a score that sits on each of these nodes, right? So for each of these states, we sum over all the incoming transitions with the corresponding alpha scores multiplied by the emission. So this hopefully makes sense. And as you can see, at each time step, like essentially for n from 1 to big N, we do this recursion, right? So this recursion, we are doing k multiplications. And we sum them over, and then we do one more multiplication on the front. So for each state, we're doing essentially k squared operations. It's k squared, not k, because this picture only draws computing alpha z as state 1. We also have alpha zn as state 2, and so on and so forth. Okay, so that's alphas, right? That's half of our picture, right? So now that we've nailed alphas, the reasoning for betas is essentially the same, similar. It's not exactly the same. So here's the recursion expression. We're not going to go through the lengthy derivation again. So the betas are called backward variables. The reason that it's called backward is that we start from the end and recurse sort of from right to left on the trilist. And the recursion equation is, here we state it without proving it, it's basically beta, again, it's a sum of all the subsequent paths that this beta could lead to via beta of zn plus 1 times the transitions that one could make from beta of zn to beta zn plus 1, and then times the observations on each of these new states. Here the observation emission probability is multiplied inside the sum rather than outside the sum, right? So in here we have essentially 2k square multiplications, but 2k squared is still the same as order of k squared. So overall, the computational complexity of the forward-backward is there are n time steps and then k squared terms in each time step, right? So this is a lot better than k to the power of n. And the secret for this basically is exchanging the order of sums and products again. You may say, how do we initialize beta at the end? We just initialize it as 1. You may say, now that we have the alpha and betas, how do we use them, right? So we can evaluate the incomplete data likelihood P of x as essentially a sum of alphas at the end state, right? We can see this is true. Basically, alpha of zn is P of x 1 through big N and the joint probability of zn, right? So if we sum over the, actually z big N, sum over the possible values of z of big N, we get P of x. Now back to our mysterious posterior variables gamma and c, right? So gamma, by definition, well, we essentially defined alpha and betas in relation to gamma. So gammas is essentially at any time step, any value of the state is the product of the corresponding alpha and beta divided by the data likelihood, which we now know how to compute here. And the C is a little trickier, right? So C, before we said you can think of it as a score, posterior score that sits on the edge. So in here, it's basically the product of the alpha on one state and then beta on the next state, on some state in the next time step, multiplying the corresponding emission probabilities and also the transition probabilities, normalized by the data likelihood as well. So this also makes sense. Kind of intuitive sense because we know that once we go from one state to another, we incur a transition cost, and then we also incur a cost of observing the particular observation at the new state. Okay, so now we've essentially completed the picture of how to do inference and learning in HMM, right? So as long as we can compute these alpha and beta variables, we can construct these posteriors gamma and C, which in turn lets us to perform maximization, right? Such as estimating the emission distributions. The mu k's are estimated as essentially the gammas times the corresponding x value normalized by the gammas themselves. We can expand this by making the p of x cancel out, or data likelihood cancel out, and write it in the form of alpha and betas. You could also do sequence forecasting. This is an example done by the book, right? So if I have observed n variables, what is the likely value of the n-1 variable of n+1 observations? So you do this by essentially looking at the alphas at the last state, multiplying the transition probability as if we were computing the next alpha, and also multiplying the emission probabilities, right? So nothing really new here. And this is how you can do forecasting for one time step. If we were to forecast on multiple time steps, then we need to basically do multiple steps of these, essentially forward recursion towards the future. So this is a recap of what we said across the last time and this time about how to do EM algorithm, like learning with an for HMM model, right? So we may make an initial guess for the parameters. Let's say pi being uniform, a being uniform, and phi somehow, right? It doesn't have to be like if the emission probability are Gaussians, we can run k-means first or run GMMs, right? So for the E step, right, there are several steps. We run forward recursion to calculate the alphas, we run backward recursion to calculate the betas, and then we calculate gamma and C from the alpha and betas, and then we also evaluate the likelihood P of X. So with the M step, we find the theta nu maximizing the Q function, and then this will give us a new set of parameters, pi, a, and phi, as described, such as this, and also last week, right? And we essentially iterate between the E step and M step until, like, for example, the parameter doesn't move anymore, or doesn't move much anymore, and so on. So again, these alpha beta algorithms or forward backward explorations, we reduce the exponential computational cost back to linear in n, right? So this is linear and quadratic in K. Again, we're using the same tricks as swapping the order of multiplication and summations. So that's the forward-backward algorithm. Is there any questions? Okay, if no, we have a little bit more to talk about to map this to some product algorithm, and also talk about max product or decoding hidden states. We're just going to sort of more or less talk about these two ideas together. So why do we care about decoding, right? You may say they have meaningful interpretations, right? For doing speech recognition, we will want to decode the phonemes and eventually the words, right? This is what our Siri or smart speaker does all the time. So given an HMM, right, so after the system has been trained, find the most probable state of the latent variable. And also note that finding a set of states which are each individually the most probable does not solve this problem. We kind of said this already. For imperfect pronunciation, then the most probable state of the phoneme is probably wrong, but with the whole sequence, we as humans can still make out what's being said. You may say, well, in the age of deep learning, why do we still care about HMM decoding? One reason that I think you should know, one should know, is that the forward-backward algorithm, or sum product or max product, is guaranteed to give us the optimal state sequence, right? Among all the combinatorially many state sequences. In the age of deep neural network, let's say recurrent neural net, or even a transformer, the decoding is done with a heuristic. It's not guaranteed to give us the global optimum because of the lack of the Markov assumption, right? So if you work with recurrent nets or these sequence models in neural networks, what's called, it's a beam search. So what's commonly used is a beam search. Basically, at each stage, we keep the top K hypothesis of what the top K likely states are. And sometimes, in a lot of cases, beam search still sort of requires us to maintain the top, let's say, B states at each time step. And then when we progress to the next step, it requires us to compute at least B squared scores, actually B times K scores, and then keep the top B again. In a lot of times, well, in production, it's a different story, but in lots of research papers, people simply set B equal to 1, like beam search or beam size 1, which is essentially greedy search over the sequence, which is nowhere near the globally optimal sequence, but it can still have reasonably good empirical results. But it introduces basically another source of distortion in your algorithm. Okay, so let's revisit factor graph as we talked about last week. So here is the factor graph of HMMs, right? So because HMM is a tree-structured graph, once we moralize it, we simply can add a factor on each edge, and we will have a tree-structured factor graph as well. Furthermore, we can simplify this factor graph by absorbing, right, we can see we can have these phi factors and the g factors. We also notice that because of these x's are fixed, so these we can absorb the g factors into some of the phi factors, right, by doing the following. So we can have an initial factor with the prior distribution of the state and also the first emission probability. And we can have subsequent factors as basically a product of the transition probability, like the product of one state given another, and also the corresponding emission probability. So we absorb the g factors into this f. If we essentially mentally run the sum product algorithm for factor graphs, as we covered last week, we can see that the factors have the following recursive property, right? Basically, the factor from Fn to Zn is a product of the factor between Fn minus 1 to Zn minus 1 times this factor that sits on Fn, which is essentially the product of transition and the emission probabilities. That looks awfully familiar, right? As we encountered quantities like this a lot already today. So this also basically says the alpha variables we're calculating are essentially the messages from the factor nodes to the latent variable nodes. So a similar expression exists for the beta variables as well. It's listed in the book. So what this says is, well, the sum product algorithm of factor graph is a strictly more general version of the forward-backward algorithm we covered. It's fair to say that it's actually inspired by the forward-backward algorithm of hidden Markov models. So there's a brief note about scaling the quantities that we calculate. It's quite important if you are implementing this, right? The problem is, so there is a section in the book that talks about it. We're just going to briefly go through a few expressions. Don't be scared by the lots of notations here. So the idea is quite simple. Namely, if we do this alpha recursion like the following, we can see that, and so these alpha things are probabilities, right? We know that if we multiply the two probabilities, imagine them being discrete, right? So they're less than 1. If we multiply two probabilities, the number is going to get smaller. And in each of these recursion steps, we multiply the alphas with some other probability. We sum over, but then this is still sort of the same order of magnitude. And then we multiply yet another small probability. So these alphas are going to get smaller and smaller as time goes. And soon enough, usually after like a couple of steps, less than 10 times steps, when we run into machine precision problems. So the recipe for this is that we normalize the alphas. Instead of calculating the original alphas, we calculate these normalized alphas that are essentially, instead of being the joint, they are being the conditional probability of z of n, given the x's so far. So as you can see, these alpha hat, z and k, they sum to 1 over k, which is nice. We know that these long joins are hard, so we can define basically some normalizing factor and then derive essentially the corresponding revised recursion expression using these normalized alphas. We're not going to go through steps. this is for your reference if you are going to implement this. And so we kind of did all this preparation to talk about the Viterbi algorithm. So the Viterbi algorithm is to find the most probable state sequence, such as, well, like this, right? We want to do this recursively. Right, from the joint distribution of the HMM, we know that this expression holds, right? And then we can design recursion. So we have this omega variable, which is essentially over all the possible incoming sequences from Z1 through Zn-1, like what is the score for the current state, right? And the recursion goes that the omega variable on step n is essentially the omega variable of step n-1 times, in here we're working in log space because of the scaling problem we talked about in the last page. So the omega variable times the transition probability and times the emission probabilities. Except in here, instead of the sum, as in the alpha variables, we're using a max. So what this omega variable keeps track of is basically the joint probability of the x's and the z's given under the most likely state sequence so far, right? And we can do this recursively. Basically, we're doing max sum in log space, and this, if we do it this way, also would not have scaling or numerical issues. So this is known as the Viterbi algorithm. If you're doing gene sequence alignment, you use this algorithm. If you're doing knapsack, it's pretty much the same algorithm. So a sort of explanation in plain English of the Viterbi algorithm is basically for each step, and remember which is the best transition to go into each step at the next step. And then right, when we recurse until the end, we find the state with the highest score, and then we backtrack. An interesting thing we do is, if among all of the like omega of z and 1 and omega of say z and k's, we take the max, and then we use these back pointers to basically at each time step when we do this max observation, we keep a back pointer. Right. Keep its back pointer as max Z-1. Basically, which of the states, previous states, led to the most best score in the current state, right? And this expression is the same. So we used to kept back pointers. No matter which state went out at the end, we use these back pointers to sort of trace back to the whole sequence, right? If it's here, we trace back here. All right. So that's all we need to say about sequential data today. An hour is enough, and I guess enough is enough. Is there any questions so far? Okay. If not, let's call it a day. Maybe be prepared to do a forward iteration in your exam. I'm only half joking because, yes, the exam would cover all the content from week 1 to 12. The fact that this week doesn't have a lab does not mean will not be counted. Okay, I'm stopping the recording right now.